Okay, now, again, to summarize, we have this cylinder. I haven't written the dimensions, but it's centered. The x-axis is through the axis of the central axis of the cylinder, and the origin right in the middle of the cylinder. And if XYZ is a point anywhere within the cylinder, then we can think of a little box around the point XYZ going to contain some mass. We have an R vector from this point to the point big X along the x-axis outside the cylinder, and we get the expression for the contribution to the gravitational field at this point due to the mass within this little box. And that's going to be this. Now this follows directly from what we found earlier in the preceding clip, and all I've done here is I've introduced to the expression that we had at that point is I've introduced the rho times delta x delta y delta z for the mass big M. And if I simply close the parentheses, we'll have the expression for the gravitational field at this point due to this increment. Okay, now we want to sum this over all possible increments within the cylinder. Now, not everybody's going to be equipped to do this, but I'm going to show what happens anyway, because not everybody's done multivariable calculus. Not everybody's used to describing various regions in terms of inequalities on the coordinate on the coordinates. Okay. The inequalities that could be used to describe this in terms of rectangular coordinates, clearly x within is within the cylinder if it falls between negative L over 2 and positive L over 2, L being the length of the cylinder and x being 0 at the center of the cylinder. And if the radius of the cylinder is capital R, which it is in this case, y can go from negative R to R. Now we can look at that. We can look at the cylinder from a point along the x-axis. It's any cross-section of the cylinder perpendicular to the x-axis is going to be a circle of radius big R, and that means that the y-coordinate could go from negative R to positive R, with the z-coordinate going from, well, if this is the y-coordinate here, the z-coordinate is going to go from here to here. And by the Pythagorean theorem, that means that z is going to go from negative square root of big R squared minus y squared to positive square root of big R squared minus y squared. And that's straightforward if you're used to doing this sort of thing, and if you're used to describing regions in terms of inequalities. If you aren't, take our word for it. For any x from negative L over 2 to L over 2, for example, maybe this x, we get a corresponding circle, cross-section perpendicular to the x-axis for that circle, and that's going to be this circle. And again, the y-coordinate could go from negative R to R, and for any given y then, between negative R and R, the z goes from here to here. Okay, that gives rise to the triple integral. Now I've crossed out lightly the yj and the zk here in terms of something we did a little further on, so you can ignore the cross out. Let's just take that as let's just take it as if the cross out wasn't there for the moment. Okay, that gives us the integral, and I wrote the limits on the integral wrong right here in front of your very eyes. I'm going to fix that. Okay, we first integrate with respect to z from the limits on z, then with respect to y, between the limits on y, then with respect to x, between the limits on x. We integrate the expression that we have here. Okay, now the G row I've factored out, so I've just got the expression in parentheses with the limits, and this is what we have. Now the empty parentheses down here is just what I've written here. I chose not to write that in class, and I could fill that in, and maybe I will at the end of this. But it's just the 3/2 power expression is just this. You should know, if you've had calculus, that sort of thing can be integrated using trigonometric substitution. I'm not going to go into the details of the integration, at least not in this clip. Okay, so here's our integral for the field. If you do this integral for a constant rho, you do get the field of the cylinder at the point big X.